Hello and welcome to part 8 of Dev Maths and Stats Refresher Course, Lecture 8. So we're finishing off now with some examples and we're going to try and rewrite these identities, and I'll do it on the whiteboard for a start. So this is the kind of thing that you'll see if people are in academic papers are trying to justify the model derivations, or in textbooks you'll see a lot of this kind of thing. So let's just take it to a whiteboard. We're going to use these rules, so I'm going to keep those rules and start a new whiteboard. So maybe I have to make it a bit bigger because that's a bit of a challenge to see for you, I think. Hopefully you can get that. So just work through these A, E. Okay. So the capital letters we're going to assume are, there might be some minor typos in this. The capital letters are all random variables. Small letters will all be scalars, just fixed numbers. So this is using the rule, obviously, that this one, e of ax equals a e of x. So it's just going to be 12 times the expected value of x. Okay, so far so easy. And let me go this way. So e of a minus b. That we're going to use two rules, which is the one we just had, the multiplying one, so multiply by -1, flips it to minus the expected value, and then the a plus b one, which is the first one we started off with, just separate them out like that. So it's going to be the obvious answer. So it's just the expected value of a minus the expected value of b for that. Okay, c, expected value of, this is like just a generalization to when you have several then it just becomes 6 times the expected value of u plus 2 times the expected value of v minus the expected value of w. That's for C. So which one's that one, that one, that one. So var of 9 worker here gets slightly less obvious because you get deceived by this one and forget that when you get to var 9y, I'm sure you don't want to hear me say it again, but I hope you're not just sitting there chilling. You must be pressing pause and trying to do this before I do it. So hopefully you've thought about this one and you see it is really 81 times var of y squared. No, var of y squared times var of y, because that squares. So there we go. On, giving a tick. I hope they're right. I'm going to have to make a new line for this one. E var of 4 times random variable g plus 4 times random variable h. Very imaginative. Be 16 times the var of random variable g plus 16 times the var of random variable h. And that's the end of the story if they're independent, but they may well not be, so you're going to be, it's 2 times 4, it's 8 times 4, it's 2 cov gh. So it's 2 times 4 times 4 covariance. Okay, covariance of a times, not times, the covariance of random variable a and 11 times random variable b. be just equal to 11 times the covariance of A times B. Because multiplying one of the variables just multiplies the covariance. That one. Covariance of 4x 2y, it's G. X, and it's 2y. You can use this idea again, so think about that. And it's going to be 8 times the covariance of xy. Okay, then this one might need to be done in a couple of stages. Give me H covariance of 2 random variables added together with another 2 random variables added together. We've seen that there's sort of distributive rule, so it's going to be the covariance of A plus B, the covariance of C, plus the covariance of A plus B, the covariance of D, with the covariance of A plus B with D. But then you can expand that further to get covariance of A, C, plus cov of A, AC and BC, plus covariance of A, D, plus covariance of B, D. So you can expand it as separate covariances and add them all up to get the overall covariance. And finally, as the correlation coefficient of, oh, it's in green for some reason, Howard. It's the green deal. A random variable with 5 minus 2y. Well, the adding 5 makes no difference at all to the correlation. Multiplying 2 makes no difference at all to the correlation, but going negative will flip it the other way around because y is now being measured in the opposite direction, so it would be just negative correlation coefficient of x and y, wherever that is. So the 2 and the 5 make no difference, but the negative one changes the sign. Okay, so that's the first of those questions. My green tick. Okay, so I hope that makes sense, but do ask. I think we might be able to just finish these off quite quickly. I know this needs a bit of writing out. Okay, to show that if 2 random variables are independent, which means you have this is true. That's really the definition of independence. Then show that if that's true, then the covariance comes out as 0. Okay. Just grab it. Go back to this overcrowded thing and clean it off. Oh, like this. Okay. So the details, you're going to say that, okay, covariance of A and B is equal to, I'm going to try and shorten this a little bit, in terms of notation. The basic definition is this. First, use small letters for realizations of the variable. I'll need the subscript as well. and that's probability of AI and, or coming jointly with BJ. So that's the definition of covariance. But for a start, let's just write it where it makes it slightly easier to handle. I could combine that, I'll leave that like that. What I'm going to do is, for the rest of the working out, I'm just going to change. I'm going to write this just to save a bit of writing like that. P of I and Pj, just to stand for probabilities of AI and AJ. So just to make it shorter, I'll do that, because it's quite a lot of stuff to write out. I'll just confuse the screen. So what you do is you just multiply out this whole bunch of stuff. So you're going to get this double summation like this. Of AI Bj times Pi, probability of I, that, times probability of that. Then you're going to get Ij, this minus, get mu b, AI, so that's this one times this one, times Pi Pj, and then kind of symmetrically the same thing. But this time it's going to be mu A from here and Bj. But again, it still times the same two probabilities. So this is simple because they're independent, it's just P, that all stands for that in every single one. And then plus mu A, mu B, times, I should be sigmaing it. Sigma E Ij times Pi Pj, which is from the last two there. But it all becomes simple quite quickly because this AI has got nothing to do with this summation, so that's be a common factor, and this Pi will be a common factor. So you can take that outside the summation, you just have this, because that's got to be it. This is only depending on I, so it needs to go there. Like that. So here, this UB is a complete constant, so that will occur in everything. Remember, all these things, you're adding stuff up, you're going along the rows and down the columns. So here, if you're going along the rows, this can wait to come out of each row and so on. Here it's just a constant, so that's a complete constant factor, so that comes right outside. That's just a constant. It goes and everything. AI only changes in each row, so that can become out there, and this only changes in each row. And this goes along each column, Pj. And a very similar thing with all the things reversed, so A. When you get to this one, we can note that you can reverse the order of summation. So instead of going along each row, I'm going to go down each column vertically by switching this around, so it's like this. So J first, and then Bj, Pj, and then going along down the column, sorry, like that, AI, and then plus sigma mu A mu b, and then I. Doesn't matter, you could just leave this really. I suppose you ought to. Pi pj. Now almost there, because this thing here, sum up ai pi, this is the expected value of a. So that there is mu a, and this is mu b minus mu b. This is mu a again, it's the same as here. And this is summing up all the pj's. So the probability of each value of bj, so that just sums to 1. This is minus mu a. That's the expected value of b, so that's mu b. This just adds up to 1 because it's all the probabilities of ai, so that makes no difference. And here, this adds to 1, this adds to 1, so you just have that part there. Separate line. If you look at this, this looks suspiciously like not a sausage. So covariance of AB with this assumption just comes to 0. It all cancels out. So covariance is quite good because it does show you when there is no relationship between the smaller the covariance gets, the closer you are to independence. But you already want correlation coefficient to give you an idea of exactly how close. Okay, these next two are pretty almost one-word answers. So if you have a read of that, pause the thing. Okay, the answer is, how would it affect the correlation he finds? Well, basically, he's got 2 sets of numbers. He's got a set of numbers for wheat harvest, and he's got a set of numbers for price of fuel, set of numbers for wheat harvest, and he's found that those numbers he's got have this correlation coefficient, so weak negative correlation. But the boss is saying, oh, go away and change these figures around. So she tells him that she do that. So, but using a traditional measure of wheat instead of kilograms, that's just going to be different units. That's going to change the scale. So the wheat measurements are going to be rescaled by a factor, and the fuel prices he's got are going to be shifted by adding on, or no, subtracting this amount. But for the 2 sets of numbers, if you change the scale of one and move the other one, shunt it up and down by this 84 cents, that will make no difference at all to the correlation he finds. So even if his boss is correct, the correlation will be completely unchanged at minus 0.325 because it's insensitive to scale, which is an advantage of it. So no difference at all is the answer. And finally, 4, hope you think about that for a moment. So if the covariance of x and y is 0, another, as we just showed up here, that means that they're independent. So y has no effect on x. So the expected value of y given some value of x, well, if x and y are not related, then having this extra information tells you nothing. So the expected value of y given a particular value of x is just the expected value of y. So it adds nothing to it. So this would just be expected value of y as the answer. Okay, some more things like that and other things on the problem sheet. And I hope that if you get familiar with this, it'll just make the journey a bit smoother when you're sort of following this kind of technical writing over the year and in future. So I look forward to discussing it in a live class, but for now, thanks for watching.